In our public key infrastructure, or PKI, we can use both asymmetric and symmetric encryption, as well as hashing, to provide and manage digital certificates. In PKI, we keep our private key secret, but we also store a copy of the key pair somewhere secure. That's called a key repository. If I just keep my private key on my computer, and the computer is stolen, even if we have full disk encryption, I still lost my private key. I can't decrypt any of the messages that were sent using my public key. So to ensure we can still access our data if the key is destroyed or lost, we have a key repository. If someone loses their private key, we should have a policy in place on how to retrieve them. Other than the obvious approval from the user and their manager, maybe even their VP, it should also not be a job just for one person. If we put a practice in place, then we need 2 security administrators to retrieve a key pair, chances of people doing something they shouldn't are significantly reduced. While it's not separation of duties, it's a dual control where the 2 employees retrieving the key would have to be colluding in order for them to retrieve keys they shouldn't. That's much less likely than just one malicious employee. Key escrow is similar to our own key repository, but in this case it's a third party holding on to our keys. This would most often be law enforcement if for some reason or other we're under investigation. If it's a server-based certificate, they're public keys signed with a digital signature. It could be SSL certificate, for instance. It's assigned to the server and stored on it. If it's a digital signature that's a client-based, that would be assigned to you and stored on your computer. If it's for SSL certificates, we most likely use a public CA like VeriSign or GoDaddy. They have the rights to issue and revoke certificates. An ORA, or an Organizational Registration Authority, works within your own organization. It authenticates a user or a system, and then issues a certificate. Issuing certificates is obviously not the only job of the certification authority. They also need to keep a check of the ones that have expired or have been compromised. For that, we use a certification revocation list. If, for instance, the private key is compromised, we would revoke the certificate. Or if an employee leaves the organization, we would keep the certificate so we'd be able to decrypt messages, but we would retire it from active use. Up till recently, this has also been used for SSL certificates, but we are moving more towards online certification status protocols, which is a client-server-side hybrid. Before, we would check every single certificate to see if it was expired, whereas with the new version, we just check is that specific certificate expired, which is, of course, much faster. And certification and revocation is an ongoing process. The list is never static, so it makes much more sense to use a server-client hybrid instead of having to go back every time and check. And while we're on the topic, let's look really quick at the Clipper chip. The Clipper chip was a chipset that was developed and promoted by the US NSA as an encryption device to secure voice and data messages. But they were smart enough to leave in built-in backdoors so they could listen in. It was basically a little chip that would be embedded in every device to secure us, but in actuality it was just for them to listen in. Luckily, after a huge public outcry when they publicized it, the idea was abandoned, which was very lucky, because after the fact they discovered a bunch of security holes in it, part of that from using the skipjack cipher, which was never secure. Digital signatures provide integrity and non-repudiation. If I want to send an email to Bob, and I want to prove to Bob it came from me, and that the email has not been altered between my computer and his, first off my email would be hashed, and that hash is then encrypted with my private key. Remember, this is not confidentiality, it's integrity. The hash, encrypted with my private key, is the digital signature. I would send the email along with the digital signature to Bob. Bob would then use the same hashing algorithm on the email. He would then decrypt my digital signature with my public key, and then he would check the 2 hashes against each other. If the 2 hashes match, Bob can safely assume the email came from me. It has not been altered. That doesn't mean it wasn't intercepted on the way. Someone else could easily have read it. This is only integrity. I can then, on the other hand, later not say I didn't send the email, because Bob can prove it was encrypted with my private key. And that is very simplified how we use digital signatures to provide integrity and non-repudiation.